Hi chemists, just a short video today. Next in our hydrocarbon series, I'm just going to cover benzene and aromatic compounds. Just a short little one, not many examples. It's only tying in with one syllabus point. Okay, so let's talk about this molecule that we call benzene. It's a bit slightly different to everything we've been talking about, but not too different. So benzene was discovered to have the formula of C6H6. Okay, it's a cyclic hydrocarbon as well. So it is a cycle of 6 carbons, and off each carbon is a hydrogen there. Okay, now it was originally proposed to have 3 single and 3 double bonds, and this will give you a nice structure, and that's roughly hexagonal. So every second one is a double bond. Now there's a couple of problems with this. There's a major problem with this. We've talked about bond length before and how a double bond is always shorter than a single bond. And a triple bond is shorter even again. So that would make every second bond in the molecule shorter. So it couldn't be a regular hexagon if that was true. So what is actually true for this molecule is that single, double and triple bonds are kind of like a good model that works fairly well for most molecules, but you know, Schrodinger's model and all that crazy see, I'm even lost for words now. Probability clouds of electrons. It's not that simple. So we can often think of it like each carbon to carbon bond is a 1.5 bonds. Okay, don't freak out of that. But electrons in this molecule do some funny things. Okay, so it turns out that these electrons in the image down below, you can see that we've got these 2 wire grids here, and they're delocalized electron clouds, or the electron orbitals for this molecule are all kind of smushed together, and there's a big pillow of them, a probability cloud above it and one below it, because it ends up being a planar molecule. So it lies on a plane, electrons above, electrons below, 2 large orbitals, one above and one below the ring. Okay, delocalized means that those electrons aren't kind of bound to one of the atoms, they're shared between the atoms. Okay, so as I was saying, 3 bonding regions around each carbon. The shape around each carbon is trigonal planar. And because these are not single bonds, they don't rotate. They're more than single bonds. So the whole molecule itself is planar, as I was just talking about before. Planar with delocalized electrons lying above and below. Okay, for these reasons, benzene is very different, in some ways, than alkenes or alkanes. The delocalized electrons are at a very low energy. It produces a very stable molecule. So benzene itself is very unreactive, and it happens a lot in organic chemistry, but we tend to and we can swap these hydrogens out for other things. And we can do reactions where we add on and make the molecule bigger, or nature does that too. So for example, here we've got a reaction that we'll look more into in chapter 10. I've just scribbled all over it though, gonna rub it out. We've got benzene on the left here reacting with bromine, and what ends up happening is, with the presence of UV light, to break some bonds, because UV light has the same kind of energy as that is in the bromine-bromine bond, what can happen is you can get a substitution reaction where the hydrogen that was here bonds to the bromine and they swap partners. Okay, we'll do more detail in that in chapter 10, I think I said, yep. So we can do some reactions with benzene, but that core 6 carbon stays the same. Okay, as I was just saying, there's a great variety of organic molecules that contain benzene rings, and we name these that contain benzene aromatic compounds. And I'll talk about that on the next slide. That's good. I was just about to go a bit deeper there. So aromatic, aliphatic, they're opposites. But as I was just saying, aromatic molecules contain at least one benzene ring in their structure. And they often, not always though, have the property of having a smell, an aroma. So initially, they were called aromatic compounds because they smelled before the chemist knew the structure of them. But as though it was, once the technology came along to investigate a bit of structure, it was like, these have these benzene rings in them. So the name has stuck around. So not every organic molecule that has a smell is called aromatic, or even a nice pleasant smell is called aromatic. It's just that we stick the name aromatic when they have these benzene rings there. Now the opposite of aromatic is aliphatic, and so aliphatic molecules do not have a benzene ring in their structure. So we don't often use the word aliphatic. We only use the word aliphatic if we're talking around about, and we're talking a lot about benzene rings, and suddenly we're mentioning something that doesn't have it. We might pull that word out. Hopefully not to sound fancy and smart. Okay, so I've given some structures of some benzene ring molecules here. And I don't want you to name these or learn these at all. It's just giving you appreciation of the range of them, okay? So here we've got cinnamaldehyde. It's an aldehyde. We'll learn about that in the next chapter. But it's got this benzene ring in there, and it's one of the main compounds in cinnamon. Gives it its scent too. We've also got thymol. I forget what that was all about. That's okay. Look it up if you're interested. Also a benzene ring. And different bits hanging off them though. Notice the bits hanging off them are different. Limonene. So in a lot of citrus fruits, especially in their pith, in their skin. Probably not a good word to say, but you know what I mean. And then we've got vanillin, which is one of the main compounds that gives vanilla its smell and taste, but not the only ones, but one of the main ones, vanillin. It's got this cyclic group, and next chapter, aldehyde, alcohol, and methoxy. But anyway, next chapter. Okay, you've also got molecules that are just these benzene rings bonded together. Naphthalene is the smell of mothballs. I wonder if they're named that elsewhere in the world. Naphthalene balls that you put in clothes, and old people put in clothes to get moths to go away. Yeah, and you've got these other ones. I forget what anthracene was used for. That's okay. You can look it up. There's structures like those. They have many uses. Don't need to learn them. Okay, there's a check your understanding there. I also need to talk about homologous series. We start to talk about it now, and we'll talk about it much more in the next chapter. But it's not too much of an extension here. So in chemistry, a homologous series is a group of the same type of organic molecule, but they only differ in the length of their carbon chain. For example, we've already considered the homologous series of straight chain alkanes, where each alkane is one carbon longer than the last. So when we talk about methane, ethane, propane, butane, pentane, and the differences in those, we're talking about a homologous series because they're all straight-chained alkanes. We'll also talk about a lot more next chapter. So a group of organic molecules that are cyclic alkanes are also another homologous series. So the cyclic alkanes, homologous series, they're the same kind of structure, but they just differ in length. So you can talk about, you can't talk about cyclomethane, that won't form a cycle, or cycloethane, but we can talk about cyclopropane, to form a triangle, cyclobutane, cyclopentane, cyclohexane, cycloheptane, cyclooctane, cyclononane. I think they're getting a bit big there, and they tend to fall apart and not be stable. They're much more rarer. We'll also talk about the alkenes. So here's another homologous series where we've got ethene, propene, butene, pentene. Okay, and there's an Androlo series there, and a modelling hydrocarbon structures. So constructing models of homologous series. All right, you can download the keynote there. Okay, next video I'm going to talk about the properties of alkanes, and we're going to do a couple of examples. Thanks for listening.